So the purpose of this video is to help you better understand a parent function's graph, a rational function, and then also we're going to focus mainly on finding horizontal asymptotes. But just a quick exploration of the different transformations of a parent function. Y equals 1 over x, with a little bit of effort, you could see that the y equals 1 over x shape would be in the first and third quadrants. We analyzed 1 over x squared the other day. And if you then apply that same kind of reasoning to graph 1 over x instead of 1 over x, 1 over x cubed, so if we increase the exponent, what does that do to the shape of the graph? Well, virtually nothing. I mean, if we draw it by hand, we would still draw it the same way. So if the exponent in the denominator is an odd exponent, it's virtually going to look the same as it does if we look at y equals 1 over x. Similarly, if we look at y equals 1 over x to the fourth, it will look virtually the same as y equals 1 over x squared. And with a little bit of effort, you can see the nuances in that. But the bottom line, guys, is that we have a vertical asymptote in all of these, in all of the graphs of all of these functions. We also have a horizontal asymptote, which we talked about when we graphed y equals 1 over x squared. And each one of these parent functions has a vertical and a horizontal asymptote in the same place. As you can see, x is not allowed to equal 0 in any of these. And with a little bit of effort, you could see that as x increases, as the denominator increases, then the fraction, actually the value of the fraction, gets smaller and smaller. So the y coordinates on the graph of each of these functions are getting closer and closer to 0 in both directions, in the positive direction and in the negative direction. So given that y equals 1 over x has a vertical asymptote right where the denominator would be equal to 0, like if x were equal to 0, that's where we have a vertical asymptote. If we were going to graph y equals 1 over x minus 1, then we would just shift the graph of 1 over x to the right 1 unit, and our vertical asymptote would be right there at x is equal to 1. Each has the vertical asymptote x equals 1. So each one of these functions has been shifted to the right 1 unit. And as you can see, just like when we were graphing polynomial functions, when we had the multiplicities of the factors, well, that kind of same kind of thing is happening here. When the exponent is an even number, the graphs, each side of the vertical asymptote goes up to the same place. And if the exponent is an odd number, the ends of the graph, as we approach that vertical asymptote, are going in opposite directions. So really, really similar to when we analyzed polynomial functions. So we don't need to spend a ton of time on that right now, because as time moves on, we're going to learn some other techniques, and we're going to continue to practice these techniques as well in graphing rational functions. So moving on to just a theorem and something that we can just refer to in a pretty simple way. If a rational function is proper, then the line y equals 0 is a horizontal asymptote of its graph. And a proper rational function would just mean when, so let's write that down, proper is when the denominator degree is greater than the numerator's degree. Greater than the numerator's degree. Numerator, I'll just say numerator degree. Okay, so that's when, as we say that's proper. Okay, so just an example of a proper rational function would be like 1 over x, like that. So y equals 1 over x, we have the horizontal asymptote, would be y equals 0. So all those functions that we just analyzed, we look at them, the degree in the denominator is greater than the degree in the numerator. So all of those have a horizontal asymptote of y equals 0. So that's kind of a helpful tool if we just can remember that. And I'm also going to give you a different way to remember how to figure out the horizontal asymptotes. And so we'll do that here in just a minute. But so in this example, find the horizontal asymptotes. Well, if you just keyed in on what we just talked about, if the denominator degree. So the denominator degree is a 2. So the degree in the denominator here is a 2, and the degree in the numerator is a 1. So if that's the case, then we have the line y equals 0 is a horizontal asymptote. So that's a proper rational function. So it's that simple for those kinds. So there's 3 different options, and let's kind of explore that right now. So horizontal asymptotes, finding horizontal asymptotes. Okay, so there's 3 options, and I like to use the bubble theorem. So the bubble theorem, if the bubble is bigger on the bottom, that would mean the degree. So the bubble is bigger on the bottom, that means the degree is bigger on the bottom. Or we have the degree on the top and the bottom are the same, or we have the numerator has a higher degree than the denominator. That would be when the bubble is bigger on top. So if the bubbles are the same size, then we just have the coefficients. Horizontal asymptote is the coefficients. I'm going to give you some examples of each of these. And then here, the horizontal asymptote is y equals 0. And here, there is no horizontal asymptote. So here's how we kind of relate this to bubbles. So bubble theorem, let's just write that down because I refer to that. There's a poster in my classroom with that. So the bubble theorem says, if you consider this fraction as being controlled by the size of the bubbles, if the bubble is bigger on the bottom, that means that this fraction is not going to float up, and away anywhere. It's going to stay right there on the ground floor, and that's the ground floor, meaning y equals 0. So the bubble on the bottom keeps, it's like if you see this kind of bubbles floating, blow bubbles with the soap, and the bubbles float around. If the bubble is bigger on the bottom, it's going to kind of fall down to the ground, and the ground level is y equals 0. So that's just the x-axis. Now, if the bubbles are the same size, like let's say we have y equals 3x plus 1 over 4x minus 2, then we would say bubbles are the same. So degree in the numerator and denominator are the same. And if we are, so if the bubbles are the same, then they float towards one real number. So you just peel off the coefficients, and the horizontal asymptote would be y equals 3 over 4. That would be the horizontal asymptote. Let's do one more like that. If we had y equals 4x squared minus 2x plus 1 over 7x squared plus 3. Well, you take so the degrees are the same, and you peel off the coefficients of the highest degree term, and the horizontal asymptote then would be y equals, make sure you always express asymptotes as equations, y equals 4 over 7. So it's that simple. All right, so easy to find the horizontal asymptotes if the rational function is proper. Easy to find the horizontal asymptotes when the coefficient or when the degrees are the same. So with the same size bubble, the degrees are the same, then you just peel off the coefficients. And it's also easy to see if the numerator has a greater degree than the denominator, there are no horizontal asymptotes. All right? And I will start a new video for the next few examples.